Hello, and welcome to this video on brewing byproducts during fermentation. Previous videos on brewing cider identified several possible contaminants at the end of your brew. This video will explore what those are and what other contaminants they could be, how they formed, and what can be done about it. Most well-prepared, pasteurized, and sterilized brews should never have any issues. However, contamination can and does occur. This happens when you have a bacterial infection, an unknown yeast strain, a poorly sterilized container, contaminated ingredients, poor aseptic techniques, or some other random event. More important than the inevitable loss of a batch of precious home brew is what happens and what you can do about it. First, the contamination may lead to methanol production. This will ruin your drink and possibly harm you. Methanol is a modified ethanol molecule and is particularly well known to be toxic. Second, acetic acid. If your brew tastes like vinegar, chances are it has turned to vinegar. Vinegar is produced by modification of the ethanol molecule. Third, fusel oils. If you are distilling and don't know what fusel oils are, you should probably stop for now. Fusel oils are the varied alcohols and volatile compounds produced as a byproduct of fermentation. Fourth, incompletely fermented substrate. In an ethanol wash, this could be sugar or dextrose. After your fermentation appears to be done, it may have had some failure, leading to the remaining ingredients not being fermented. Fifth, bacteria. Simply put, this is a nutrient-rich environment, and they will proliferate at an exponential rate. This leads to a bacteria-rich brew, which can be toxic and dangerous. Sixth is yeast. Yeast that does not flocculate and sink to the bottom can contaminate your wash. Finally, lactic acid. A similar product as occurs in natural yogurt, but incredibly undesirable in a home brew. Methanol is a relative of ethanol in chemistry and also known by the names of wood alcohol and methyl alcohol. Given the chemical formula CH3OH, it looks like this. It is a common chemical reagent. Unlike ethanol, methanol is not commonly manufactured from sugar-rich sources like corn. It is produced on an industrial scale using carbon dioxide and hydrogen. Like its relative ethanol, methanol is highly volatile. It transitions to a gas quickly and burns. Methanol can be found as a lab reagent. Here it is used as a solvent. Considering this, it is foreseeable that methanol will be poisonous to humans when consumed. Approximately half a teaspoon leads to blindness. Methanol is generated in the largest quantities from fruit-based washes. This is caused by the complex media that is fruit. In the case of fruit, fruit contains pectin, and this is why wine is notorious for methanol when distilled. Pectin is made of methyl esters of galactose. Breakdown of galactose molecules releases the methyl component which binds to water molecules. But it can occur when an ethanol wash is run too hot for too long, or in other words, over-fermented. It can also occur when pectin or pectin enzymes are added. The final possible pathway for methanol production is as a byproduct of over-ethanol fermentation. When a volume greater than 12% alcohol by volume is aimed for, the probability of generating methanol increases. This occurs at a commensurate rate. Ethanol dehydrogenation converts the ethanol molecule into formaldehyde. This into formaldehyde, which is subject to alcohol dehydrogenase again, which forms methanol. To dispose of methanol, you can concentrate your brew via distilling it, if it is legal where you are located. This removes any alcohol below 79 degrees Celsius, and a good rule of thumb is to discard the first 100 milliliters regardless of whether you suspect methanol or not. Alternatively, using minimal amounts of material that contain pectin and avoid over-fermenting. These are the only reliable means of acetic acid is a concentrate of white vinegar, or more accurately, vinegar is acetic acid at a standard of 4% by volume. When the contaminant Acetobacter, gram-negative short-row bacteria, gets into your brew, it can take the acetaldehyde, and having reduced it, Acetobacter makes acetic acid. This is then converted into acetyl-CoA, and then used for energy within the bacterium. However, if it does not convert it to acetyl-CoA, it remains acetic acid. To deal with this, the wash must be handled in an airtight container. The use of an airtight container and airlock will do this. Acetobacter can only operate under conditions with ready-to-access oxygen. Fusel oils are also known as fusel alcohol or fuselol. They are a group of alcohols separate from the more easily separated alcohols. They are largely identified by a strong odor and or taste in the brew. They contribute to the palate of the brew, and they are byproduct of fermentation and ethanol production. They occur in small amounts regardless, but a warm fermentation can increase their prevalence. This is also why methanol is part of the fusel alcohol family. To deal with this, several things can be done. The first is control the ingredients going in. Use of ingredients that you are familiar with or the recipe calls for will give you a predictable result. This produces a predictable palate. For example, knowing how much heat is in a chili when you are cooking allows you to select the right amount for the desired result. Similarly, most established recipes have a similar rationale to them. Next is the balance of the ingredients, which can mask the flavor profile. Adding another component, such as hops and beer, can counteract or cover the flavor of fusel oils. Again, distilling is an option if you can legally do so. Distilling and separating the first and last part of the wash will remove a large part of the non-ethanol component. The final option is aging. This is dependent on your beverage. Beer, wine, and spirits can be aged. Cider and similar beverages do not age as well, but this may take years, but a minimum of 6 months is required. Next is an incomplete fermentation. This generally occurs for several reasons. The first is temperature. A sudden spike, drop, or sustained change in temperature can stall yeast, leading to a stalled fermentation and eventually a wasteful exercise. The second is the inexplicable stall, which can happen when pH, cofactors, and more suddenly cease or run out, or any number of other reasons that are simply inexplicable without your knowledge being able to fix. These two leave considerable amounts of the medium that you are fermenting unfermented. For example, higher temperatures than a yeast strain can normally deal with leads to a lower threshold for ethanol. This stops the fermentation early. Lower ethanol means higher sugar, there being an inverse relationship. This can sometimes be fermented out by moving the brew to a cold environment or by pitching another lot of yeast in. The first is the accepted process for beer, particularly lager. The cold environment slows down the metabolism and allows the yeast to process more, or at least continue its processing of sugar into ethanol. The second solution is considerably more taboo, as it involves opening the fermenter and effectively jump-starting the brew. Doing so in the early stages is generally harmless, but in the latter stages can introduce contaminants and oxygen, leading to the topic of this video. Next is bacteria. Bacteria in your brew should be obvious. The cloudy, foul-smelling liquid you pour out is bad. The most common cause for this is an incomplete sterilization, contaminated ingredients, or poor aseptic technique, possibly a combination of all of the above. The first and last are simply fixed. Use of sterile equipment and a clean environment will minimize the chances of contamination. Even if another microorganism was to get into your brew, it would not be able to outcompete the yeast. Yeast will then take care of this by making ethanol. The second point is an issue. Mead and cider can be sterilized via pasteurization. Honey is heated until it is viscous, and then some for an extended period. That, coupled with the natural antibiotic properties of certain honey types, makes this a formidable opponent for contamination. Freshly pressed juice needs to be sterilized, as fruit can stand either exposed in the orchard or in the market for extended periods of time. It accumulates bacteria, and these colonies grow. Pressing the fruit washes these into the juice. Much like pasteurizing milk, this keeps it sterile or close to. This gives the benefits of good aseptic techniques and prevents the yeast from being outcompeted by other strains of bacteria. The brewer wants yeast in their brew up to and until the process of fermentation is complete. After this, it is a contaminant and unwanted product. It affects taste, feeling, and look. This can happen when it is shaken, the fermentation is not complete, or the density is too high. Seen here is a sake brew. The significant white part in the lower part of the bottle is a combination of yeast and rice, while the top half is cloudy from the yeast in suspension. To fix this, you can do the following. Racking it into smaller bottles, this siphons off the top, removing most of the yeast, and for some people this is enough. However, if you are a perfectionist and you want your beverage to look the best it can and taste the best it can, you can move the primary fermentation into a cool location to cold settle out the yeast. Alternatively, a combination of racking into smaller bottles followed by cold settling can be used. If these have been unsuccessful in previous batches, and there is one last method available to you. This is calcium, specifically cheese-making calcium. This allows yeast to flocculate together and sink to the bottom of the brew. The addition of a teaspoon or so in 25 liters is more than enough, as it is only an aid. Wait a day after adding it, and return the next day. Siphon, rack, and cold settle. These three treatments should remove the bulk of any yeast that you have in your beverage. The final particularly notable contaminant is lactic acid. Lactic acid fermentation occurs primarily in anaerobic fermentation of things like sour beer, yogurt, and kimchi. It occurs as a byproduct of oxygen shortages. Lactate dehydrogenase facilitates this, and in many beverages it adds flavor to the brew and food, as it is meant to. Lactic acid in this case is not necessarily a contaminant, but something that needs to be well balanced for a desirable outcome in most cases. You can compensate for this by the inclusion of a buffer like carbonate, and this helps to neutralize the acid, balancing the flavor profile of your beverage. Thank you for watching this video on unwanted byproducts. Hopefully it has been helpful in your brewing. Please post any questions, suggestions, or comments below.